Alright, so I've been meaning to do a PLL fundamentals theory thing for a while, and I saw Pete from TRX Bench, Peter rather. He did a little PLL theory thing on an ICOM amateur radio he was repairing. So, and he touched upon some of the theory there and some of the aspects of it, which some people found helpful, and it's something I've been meaning to do for a while. I had it on my list of videos to make, and so I thought, right, I'm going to sit down now and I'm going to do the theory one. Right, I'm not going to go too deeply into it. I'm going to try and keep it as simple as I can, but it can be quite a complex subject. I'm not an electronics engineer. I'm a hobbyist, so I've just figured this stuff out myself over the years. And PLLs, because it is a loop, it can be confusing with understanding what's actually going on. Now, I have actually done a video previously on a Cobra 25 which I was repairing, which had a blown PLL. I will stick a link down in the description to that video, and probably a little pop-up thing on the video as well, to link to that, so you can actually have an example of me actually troubleshooting one in real life and showing what I do to diagnose it. Okay, that may be helpful to you also. Now, this is a data sheet for a PLL which I'm using in my conversion board, which you probably would have seen in videos for. So the MC145 170 PLL, which is currently my little toy. This looks extremely complicated. It really isn't. A lot of these things, if you're not using them, you can completely ignore them, pretend they're not even there. Okay, so when it comes to PLLs, PLL means phase lock loop. All it's doing is comparing two signals and outputting a correction voltage. Right, that is it. Now, fundamentally, that is all they do. What you have though is, in turn, a PLL itself is multiple segments of function. So one function is an end divider, which gets the encode from the channel selector, and whatever the format that is, it may be through a ROM conversion, so it's got like a random-ish input from a channel selector, and that will convert that into a binary internally, or it's a direct binary input, or possibly a BCD input, depending on the PLL itself, which tells the end divider what to divide the frequency by. Okay, there's also a fixed reference divider, which it comes off the reference oscillator, which is usually a 10.24 megahertz crystal. That's either directly on the pins of the PLL with it using an internal oscillator, or it's fed in from a external oscillator on the board and just fed to the PLL section, like on a Cobra 29 for example. It's got a 10.24 megahertz crystal elsewhere on the main PCB, which runs the whole radio. Basically, it's mixed in various ways and things like that. So, but that's fed down to the PLL section to generate that reference, which is used here. Okay, and that's got it's got a reference divider, which is a fixed value that's inside the chip and it doesn't change. In most cases, in this particular chip, it's configurable. Right, so this is making it more complicated than it really is. Right, this bit here, say R counter, right, that's the reference divider. That is normally a fixed value. It's either 5 kilohertz or 10 kilohertz in CBs anyway. Alright, this is all relating to CBs. This is what I'm focusing on. So that's a fixed value, so it will divide that by either 1024 to give 10 kilohertz steps, or 2048 to give 5 kilohertz steps. Okay, I don't have a calculator I can pull up, actually. I probably should do. I don't think I can. Hold on, let's have a look. Can I do that? No, I can't. Won't let me do it. So if you divide 10,000, well, 10.240 megahertz by 1024, it gives you 10 kilohertz, right? Which is the reference it's using. Okay. That is then fed down to the phase detector section here, or phase comparator, whatever you want to call it. Now, say, could it be 10 kHz or 5 kHz, depending on what step sizes are being used. So in some radios use 10 kHz steps, such as the MB8719. You can do an MC145-106 is generally uses 10 kHz steps, but it can be configured to do 5 kHz steps. There's a pin option on the outside for frequency select, so it can actually have it's got an input on there. But we'll go into that when I go into my simulator thing. So that's that part. So all you remember is that it's two comparators. It's comparing two frequencies and correcting it, or trying to correct it. Okay. So at this stage here, it gets the oscillator, gives a reference frequency. Right. It's a fixed frequency. It's 5 kHz or 10 kHz. Once you understand that section, that makes this bit simple, right? Now, on the end counter, this is a little bit different, this thing, but the end counter is where the channel selector basically connects to. Okay, so it gets the frequency which is coming in from the VCO here, divides that by whatever the end counter is. So that will then output a frequency which should match the reference frequency up here. Right. Now this is where it gets a little bit complicated, because it's a loop. The frequency that comes out here isn't necessarily 5 kHz or 10 kHz, or whichever is required in order to match the reference. Right. Wherever that reference is, this will be on the output. This is all internal to the chip. You don't see any of this, but understanding how the chip works makes you understand how the rest of the circuit works. Okay, so what we have, because it's a loop, all it's dividing is this frequency by that count. Say if you're putting in 910 kHz, right, as an example, from the FN signal from the VCO, which is divided down. It will divide that by whatever the encounter happens to be. Now, for a 10 kHz step, the encounter will be 91. Right? Because 910 kHz divided by 91 gives you 10 kHz. Right? So you can predict what the FN frequency will be if you know what the encounter is, and if you know what the reference frequency is. Okay? So if you know it's a PLL uses a 10 kHz step internally, and you know what the encode is, then you know what the frequency in must be, because it's 10 kHz multiplied by the end count to tell you what the FN is. It's the same thing. You can work it backwards. You can go either way. Right? It's all just mathematics. And it's not hard mathematics either. It's all simple stuff. You just have to understand what you're trying to achieve and how to go about it. And once you understand the blocks of it, then it is just blocks. And then it's far simpler to actually comprehend what's going on. Alright, so as I was saying before, we've got the reference counter coming in, which is the reference frequency. Let's go to this one here. Alright. This is, say, a more complicated PLL than you'd normally come across. And then you've got the end counter, which also goes in. So you've got 3 different blocks in this case it's using. Right, this particular PLL's got 3 blocks that it controls. It's got 2 types of phase detector circuitry, so we can completely ignore one of those. We're not using that one. We'll just look at this one here. Okay? And then you've got log detector as well. Both of these are applicable to all PLLs. So basically what happens is it compares the reference frequency, which should be 5 kHz or 10 kHz, against the frequency coming in from here. Now, like I said, this is not necessarily exactly 5 kHz or exactly 10 kHz. It could be, out a bit. It could be wrong. When it's wrong, this phase detector here senses that error in frequency. If it's leading or lagging in pulses, because effectively that's what we're doing. At a higher frequency, the pulses are quicker than on a reference. and so it's leading the reference pulses. When it detects that, it outputs a correction voltage or lack of voltage, depending on how it's configured. It'll either reduce or increase the voltage going to the VCO to change its frequency. Right? The same thing if this frequency here is lower than the reference frequency. The pulses will be lagging. It'll be longer pulses. Well, the pulse times will be longer than the reference. They'll be lagging behind it, and so it will sense that and try and increase the voltage generally in order to increase the VCO frequency to bring those pulses into time. So, and the lock detector is also doing a similar thing. It detects if they're out of lock. If those pulses aren't lined up and they're not exactly the same frequency, the lock detector activates and turns off whatever functions on the radio. It might be transmit, it might be receive, it might be the whole thing. Right? Depends on the radio. But that's how that functions. It checks for those pulses being in time. And those pulses, again, are just those frequencies matching. If those frequencies don't match, the pulses don't match. Okay, think about sine waves. So you've got two different sine waves, a 5 kHz sine wave and another 5 kHz sine wave. If you put them together, they're going to line up. You overlay one on top of the other, and you look like one sine wave. Okay, that's basically what they're looking for. Right, so let's pull my CB simulator up, and I'll just try and explain a bit more about this theory. Okay, so let's go to the MBH 719 and look at the actual simulator section here. Now, this is basically what I was explaining. So in here we have a reference frequency, which is 10.24 megahertz, comes in, and this is, in this case, is a 10 kilohertz internal step. So it's divided by 1024 internally. Right? So that divided by 1024 gives you 10 kilohertz. Now, and here is the N divider. So that's the encode coming in. This is a typical encode channel, in this case 79 for channel 1 on the US FCC band. Okay, so channel 1 is 79, which comes into this divider. So that divides by 79. Whatever this frequency coming in is, it divides it by 79, and that will output a frequency. So what it does is this phase detector is putting a correction voltage out to the VCO to adjust the VCO frequency, and because it's a mixture of this frequency here with an offset frequency. Now this is from the, in this case it's the 11.325 megahertz crystal in this particular radio. It used to be from a Cobra 148, which is what I'm currently playing around with. And that is mixed with the VCO, and between mixing this frequency here, which is the loop frequency, with the VCO frequency, gives you the downmix frequency, which in this case is the FN back to the PLL. Okay, which is where that comes from. It's that frequency mixed with this one. So deduct the VCO frequency. Well, deduct that from the VCO frequency, gives you the frequency goes back to the PLL, and that should be the same as the encode. If you've got 10 kilohertz steps. If you have 5 kilohertz steps, the encode should be twice as much. Okay, I'll show you that in another PLL in a minute. Alright, so that's how that basically that's mixing and the VCO section works. And the frequency coming in isn't fixed, but what's happening is the PLL is controlling the voltage to the VCO so that it receives the correct frequency. So if this frequency is wrong, it sends voltage out to adjust the VCO frequency until this frequency is correct. So when it divides that down by this number, these two frequencies are both the same. That frequency internally is always 10 kilohertz, and this one here is always 10 kilohertz. So therefore they are both the same, they'll be in phase, and the phase detector say that's fine, it won't do a correction voltage, it's then locked, lock detector's okay, so the radio works, and your VCO is on frequency and stuff like that. Okay, so that is how that works in this case. If I go to a PLL which has got 5 kilohertz steps, there you code between 9 limited PLL, right? It says using all the code between 9s. These use internal 5 kHz steps, right? But functionally it works exactly the same way. So you got a 10.24 MHz reference coming in, which is from this is somewhere else on the circuit board, not right by the PLL as it is with the code between 148. Sorry. So it brings in 10.24, divides that by 2048 to give 5 kHz. Okay. Again, we need to get a 5 kHz matching frequency here. So it divides whatever the encode is. Well, it uses the encode to divide whatever that frequency is to get 5 kHz. So if you do, you know, in this case the encode's 273 on channel 1. So that's what the encode is. So 5 times 273 is 1.365 MHz. Right, that's where the downmix is. So these all have to always match. But because this is using 5 kHz steps, this number is always going to be twice that. Okay. Because it's 5 kHz. And if you put like a decimal place somewhere, or call it kilohertz or whatever, right? But it's always double that value there times 10. Let's think of that way, okay? Times that by 10, and it'll be double that. Yeah, it's I don't know, decimal places. I'm confusing myself here now as well. But yeah, that's always twice as much. Like if I go back to that MV879 again, because I'll probably just confuse everyone by saying that. Right. This is not counting this right because I haven't loaded it right. So 79 and 79. Okay. So 10 times 79 is 790 kilohertz. Okay. If I go back to the 29, 5 times 273 is 1.365 megahertz. Right? Think of that as kilohertz. Again, the same thing. It's got a mixing here. Now the difference for this particular PLL, if I pull up the database here, I'll show you that as well. Looking for 29s. This round. So this PLL has a half R output here, which is pin 10. Half R means half reference. So over here on pin 13, we have that 10 megahertz coming in, 10.24 megahertz coming in that pin. This has got an internal divider divided by 2, which means half R, which then puts out 5.12 megahertz, which then goes through a tripler circuit in this particular radio, which then is 15.360. Right? You mix 15.360 megahertz with the VCO frequency, you get 1.365. Pretty clever stuff, eh? Right? But the issue with PLL theory is that if something isn't working correctly, you don't know where to start. Right? Well, not easily. I mean, it may not be obvious where to start. Because it's a loop. If something's wrong with this frequency, this won't work right. This will be trying to correct for it and sticking either a full 5 volt out or 8 volt out or nothing. Right? It'll just be on or off, pretty much, if this frequency is way out of whack. Or, if there's an issue with the VCO, again, this frequency will be way out of whack and you get the same thing. If there's an issue with this frequency here, that frequency won't make sense. It'll be trying to correct for it. Right? If the encode is wrong, it might, in some cases, this is like a ROM control PLL on this one. So it's got there's an extra stage in here which is included on this diagram, but it converts the codes. But the actual it only allows a certain code range rather. If it's outside the range, it will lock it up. Right? Other PLLs, it will just change frequency. It'll be fine. But so there's all different things. If you've got an issue with the PLL itself where it's not outputting a correct voltage here, this will be wrong, and so this will be wrong, and then this will be wrong, and you just don't know where to go. So as you can see in my Cobra 25 troubleshooting video, which I did some time ago, I'll link that in, I actually intercept the voltage from the PLL. I disconnect it from the VCO, and I manually control the VCO, right, injecting my own voltage, which means I can actually generate any frequency I want. Within the capability of the VCO at least. Okay. That all that does is it proves whether the VCO itself works correctly, and it also means you can check this frequency here to make sure that it's being downmixed correctly back to the PLL, that FN frequency. You can verify that makes sense. You can also have to make sure that things like the encodes going to PLL are correct as per the requirements of the PLL and the particular radio. So if the encode is wrong, so it's got a bridge trace or something like that, or there's a broken connection, or a bad solder joint or something like that, this could be wrong, which throws the whole lot out again. Right? But it's all about mixing these frequencies together. It's all mathematics, and it's not hard mathematics, right? The actual PLL theory section, As long as you understand how the PLL internals work, and this is really simplified, but that is the basic function. That frequency is compared against this frequency, right? That's a fixed frequency, which is why it's called a reference, and this is the encode divided frequency, right? So wherever this channel frequency happens to be, these frequencies change, right? So there you go. Let's do channel 40. Okay. So that's channel 40 there. So that's the VCO frequency, channel 40. That hasn't changed because that's just the reference loop frequency, which is generated from the PLL's reference. Okay. Back out of this half-hour pin. Say 3 times. So this explains a bit more detail. So 10.24 comes in here. It's divided in half, which gives 5.12 megahertz. 3 times 5.12 megahertz is at 15.360. Right, which just want to make sure I cover that correctly. Mix that to VCO, gives you the downmix frequency, which just then divides by 361 to give 5 kilohertz. Right, so it's that is it. And as long as these both match 5 kilohertz, the phase detector will be happy. It won't be sending out much in the way of control voltages. There's always some little pulses and slight tweaks going on all the time, but it's just minor correction voltages. So as long as that's working, then that's all good. So this voltage here, when it's locked, will be somewhere in between the PLL's supply voltages. So 0 volts and whatever the supply voltage might be, right? This one here is VDD here, right? Usually that's 5 volts on this particular PLL. It's 5 volt supply. But you also have to allow for the fact that it doesn't go rail to rail. So it doesn't go fully to 5 volts. It's got a gap in what it can actually supply. So I think it's about 4.6 is the absolute upper limit of what this PLL can put out for a phase detector correction voltage. So the phase detector output is this pin here, pin 7E. Right? That's what PD means, phase detector. And that's the correction voltage. Right? And that downmix frequency here coming in, I keep saying FN, well that's FN pin there, frequency in. That's what that stands for. So yeah, and that's all it's doing is correction voltages. So it's got to be somewhere between in this case VDD and VSS, right? 0 volt and 5 volts. But the closer to the center of that range, the better. Now this radio, just to complicate things a little bit more, this one has a TX RX offset, which is why it's got a 5 kilohertz shift, a 5 kilohertz step internally, right? So if you look, if it's changed by one channel on here, the encode is changed by 2, right? See, it's gone 359, 361. That's one channel because it's got a 5 kilohertz step. So it's actually doing 2 steps per channel. That's the way it works. And if I switch to RX, I'll go to channel 1 again just to simplify things. Okay, so back on channel 1, 273 encode. There we go. Stick on RX. Now you see the channel frequency has not changed because you're on receive, but RX uses a different encode because internally to the radio it's got a internal an IF frequency, internal frequency, right? And in that case, it's 455 kilohertz, which is an IF offset for the receiver, for the decoding of the receiver signals. Okay. So over here, 455. So that's what it needs to generate. And so in order to get that, it needs to offset the VCO frequency so it can add that frequency on effectively. So it runs a different frequency. Right, so there's TX frequency here, or TX VCO frequency, and there's the RX VCO frequency. You'll see they're 455 kilohertz apart. Okay? And you'll see resultantly the FN frequency is also 455 kilohertz difference. Right? Because this frequency hasn't changed. So if this one changes, so does this. And what the PLL's got on it is a TR pin, transmit receive pin, which is on pin 9. And that is how the PLL knows whether it's in transmit or receive, and it offsets, it then accepts the other encode instead of blocking it in this particular case. It lets that through and then uses that divider frequency. So in this case the encode becomes internally 1.82. Now don't forget, these are internal encodes. Alright? That encode is internal to the chip, really. It should be inside that block really in this case, but that's the encode which is being used by the program divider. Let's say this particular PLL has a ROM encryption in it, so it only accepts certain encodes and it converts them internally. Alright? So if I pull up the encodes chart, there we go. These are the encodes it actually uses. Right? So that's what the PLL will see on its inputs. So pin 1 is this one here, right? And I've actually got extra digits on it which doesn't use, but that's pin 40. That'd be pin 6. It goes up to it on that. Yeah, something like that. Yeah, it's got 6 inputs, so you've got 6 here. Alright, so it's only using 6 digits. So effectively on channel 40 it's seeing all lows, right? Because that bit's not being used. Alright, which is how that encode is different from what you see on the channel selector. That's generated internally to the PLL, is converted internally. So it sees that, you know, 1, literally binary 1 on channel 1, and it converts to 273 before it shoves it to the program divider. Okay, that's how that is working. That's why what you see outside the chip doesn't match what's going on outside the chip. Right. This is one of the more complicated PLLs to actually deal with because it's got the switching, the internal ROM, and that sort of stuff. So I wanted to show this to show the 5 kHz steps, and it's such a common radio. You know, it's something which is going to come across by a lot of people. So we'll go back to the MV8719 and go back there again. Again, same deal. Right, so if I come back over here, go 719. There's the pinout for that chip. This has got extra bits on the phase detector. It's got amplifiers and filtering. You can basically treat all those as phase detector. Alright, so the phase detector comes out, goes in here, gets amplified and filtered, then goes to the radio. Alright, so that pin there is basically going to here, to the VCO. Right, it's makes it a lot more complicated than it really is. It's not. There's all sorts of maths and stuff involved with that, which I don't have a clue about. It's not something I've ever gone into, and I don't really need to because, you know, it's just not necessary. But on this particular PLL, because it doesn't have a ROM, whatever you put onto these pins is what's on here. Well, it kind of does. It's got an inverter inside. It's not really a ROM, but it's an inverter here on that pin. So in this case on channel 1, that's the encode, right? 79, and that's the binary. So it's treating it as though it's got 7 bits. Alright, it doesn't have 7 bits, it's only got 6. externally. Pin 10 is an inverting, so it actually works backwards from what you expect. Alright, so anyway, it's it's a bit interesting, but the way they work it, but when pin 10 is high, it's actually low, and when it's low, it's actually high over here on the 128. But yeah, it all works the same way, and that's it. So that's how they function. Reference comes in, it's compared with the N divided frequencies. That divides that frequency by the encode, compares the two frequencies, sends out a correction voltage. I mean, that is basically how they work. Right. So I think I've waffled on enough about that. It's been quite a while. I think my throat's really dry. So why do I want to talk so much when I've got a sore throat? I don't know. It's strange. Okay, so yeah. So if you're interested, then have a look at my other video, the Fluke 25, which I'll link in. And if you think that this bit of software of mine will be handy for you, you can get it. If you do a search for Defpom CB Simulator, you'll find it. I've got it for OS X and for Windows as well, although I haven't updated it, so it's probably I think it will still work on the latest versions of Windows. I can't say I've tried it. I use a Mac, so I've built Windows versions, but they're not as thoroughly tested. But it does work. Right, so you might find this helpful because you can simulate all different PLLs. UPD858s. You can change frequencies, like on the like this. I'll go back to this code 148 I'm using here. My code 148 has got a different crystal in it. Well, it did have. It's got that one in it, right? Which is 11.1125 tripled. Okay, so you see what happens when you put a different crystal in, and do a calculator and tell you what frequency you're going to get, that kind of thing. But it allows you to actually create different radio configurations. So if you know what PLL is, this is default configurations, but you might have a radio that's got a different IF. Might be that IF or something like that. Something else could be different, but it depends on the radio and stuff like that. So yeah, it depends a lot on various things. But I've tried to put a lot of configurations in, but UK radios as well, PLR2As, of course. But it shows all different configurations I have. But yeah, what else is in here? Encode converter, convert encodes. If you know what the decimal is, so 79. There's binary. This is in reverse, so this is software that does a conversion. It goes MSB to LSB, which is the way it's supposed to be done. That's like the standard. But when I do this kind of thing, I actually go LSB to MSB just because it's just easy to understand in most cases. But anyway, right, that's enough of me waffling. Hopefully you understand PLLs a little bit better and how they function. Yeah, I think that's it. My voice can't take anymore. Have a good one. Catch you later.